So you heard that I'm one of the Cython maintainers, project co-founders. So Cython has come a long way. It's been around since, well, the early starts have been around 2002, actually. The project was, back then it was called Pyrex. Probably no one knows that name anymore. In 2007, we forked that project and it became Cython. And since then, it's been, well, hugely developed. There's been a lot of features coming in there. And it's also become a lot more like Python since then, which it kind of was before, but not that much really. So what is Cython for those who have never heard the name? Cython is a Python compiler. So you can throw a piece of Python code into it and it'll compile it into a C extension for Python. So you get a binary module out of it that you can then import into Python. And the way it does that is, well, as I said, you can just throw normal Python code at it, but you can also add type annotations into that code, and that will allow the compiler to adapt the code to more specific data types than the generic, this is an object that you know from Python. And that way you get very tailored, very optimized C code, which can be as fast as any C code you would write out there. And that's the cool bit. You can write all that in Python and still get fast C code out of it. Just to get you an idea about how this looks, here is Jupyter Notebook. Probably all of you know this. If you don't, look it up. It's worth knowing. Jupyter Notebooks support Cython directly, as they do many other languages aside from Python. So Python has been the original language that Jupyter Notebooks were supporting. Actually, that IPython notebooks were supporting. And nowadays, there are a lot of languages, including Julia, including even C and C++, that you can write into Jupyter Notebooks and have them, compile the code for you. But you can also write Cython code in there. In order to support Cython, you can just say loadx Cython, and then it knows what a Cython compiled cell is. And just to make you see what I'm using here, I'm using the latest C Python non-release. So there's beta 1 isn't out yet, but that's what current 3.10 branch gives you. And I'm also using the latest Cython development version. There will be an Alpha 10 release soonishly. I've already been preparing that for a couple of days now. It didn't work out that well, but it'll be out soon, before Christmas. So there's an A9 that you can use, but A10 is, as always, much better. So what does Cython make of your code? The first thing you'll notice here is I start the cell with %Cython, making it a Cython compiled cell and not a Python cell. This was normally running in Python. So this is now getting passed into Cython, and Cython will compile the cell for me. As you can see, it's regular Python code, just a simple function, another C function with a type declaration in it. And you notice that it's not just Python int, it says something like Cython.int. I'll talk about that in a minute. You can declare static variables and do the normal stuff that you do in Python as well. And now I can run this cell. It'll take a bit longer to run because it gets compiled. And then there is some output. Why is there some output? Because I asked it for an annotated version of my code to see what Cython actually made of it. If I take that out, I'll get nothing, and no output at all, because it just gets compiled into a regular Python extension module. With -a, I get just a copy of my code as HTML output, and then I can click on one line and it tells me the C code that line generated. Okay, so lots of C code. You probably don't want to look into that much, but this is a nice way to see what Cython generates from your code. So you can just see, there's stuff in there. There's some C API calls that allow Cython to do object operations. And a lot of this will actually be regular C in one way or another. So it compiled a couple of functions for me. So let's use one of those. Add one. What would you expect? Well, that's 6. Not surprising. So I can just call these functions now from Python, from Jupyter, and they actually get executed. What gets executed is the C code that you saw in here, right? So that's now native code being executed here for these functions. A bit more about functions. You've seen regular Python functions in here. That's like this. I can add type declarations, which then unpacks the argument that I get into, in this case, cint, right? So usually a 32-bit C integer, whatever it is on your platform. So Cython.int is a C integer. Don't have anything else here, okay. But then inside of this function, when I compile this and actually say -a, then I should get the HTML output. And then here you can see that the x+1 actually now translates into normal C code. So that is a plain C operation now, right? Because as I said, x is actually a C integer. Okay, a bit more. I can turn a function into a plain C function, so not a Python visible or Python executable function, but a plain C function by adding the cfunc decorator. And I can also say I want something that is fast callable, so as a C function callable from C here, and at the same time Python callable, so that adds a fast a fast C level or Cython level call interface to the function, but still keeps it callable from Python. A C function, that's a static C function. It does not have a Python interface, and so it cannot be called. When I try this, it's going to tell me name error not defined. Okay. Okay. Calling C functions. So since all of this translates into C, it's trivial to call C functions from this. In fact, I can just say, I need libc math, and I'm going to take the sine function from libc math and the pi value, and then I can calculate pi by 2 and the sine of that, and print the results, and unsurprisingly, that's 1. Okay, so this is, again, running completely in C, as you can see from the expression here. So sine MPI divided by 2, the whole expression turns into a C expression. Okay. You can use memory allocation. You can say I call malloc here, malloc on free. What you shouldn't forget in that case is raise a memory error if it goes wrong, right? So I really like this part. You say malloc and then you do something totally Pythonic like raise memory error, right? Very nice in Cython, and all of this chains and combines nicely. So you can freely mix C features and Python features. Okay, and then for a longer example, let's say you want to wrap an external library. So here's Lua, for example. You declare a couple of functions defined in Lua, and then you can just write code that creates a Lua runtime with the corresponding C API function. Loads some code in there, calls, executes that code, and then gets a number back and all that, right? Okay. C arrays, just in case you've written a bit of C before, C arrays are very nice in Cython. You can slice them, you can assign them by value, you can do slice assignments. You don't need all those for loops in C anymore. You can just use Python features, normal Python syntax features to work on them. And you can also use C++ in the same way. For example, if you want to use a C++ vector, I can import that. Obviously, this code is not executable in Python, right? Because there's no such thing as C++ vector in Python. But once it's compiled by Cython, it's native code. It runs in C++, uses C++, and then it all just works. So here I'm creating a new vector, doing some, copying some values, looking at the values, doing some stuff in there, and then I can call that function from Python, and I get something back. Right? I actually get a Python list back because that is what vectors automatically turn into when I want to ask for a Python object from them. If you have questions along the way, it's probably best to put them into the chat. I'll look there from time to time whenever I, remember looking there. So feel free to ask in the middle, or I'll try to keep some time in the end to ask open questions. Okay, here's a notebook. I've already shown this a couple of times on other conferences, venues. So in case you've already seen something like this, sorry for that. I updated it a bit, as I usually do, as new features come into Cython. And in Cython 3, one thing that we've focused on a lot is making it look a lot more like Python, especially the type annotations. If you've used Cython before, you probably ran into all the cdef something somewhere. So there's a special syntax in Cython that we used, or actually still use, but that was kind of the normal syntax in Python, in Cython, to add type declarations, and now you can be a lot more Pythonic and use Python type annotations everywhere, and it works quite well. So again, in that notebook, I activate Cython support, and then let's look at what I have. Again, Python 3.10, Cython 3 latest. I have NumPy and kind of a not so recent, but kind of okayish GCC version.
There is a question in the chat. You might have a look at it.
Yeah. So question is, what platforms do we have available as a compilation target? It generates regular C, and C tends to be portable all by itself unless you do something stupid in it, like assuming that a C long is 64 bits, which it isn't always. But unless you do something like that, it should be all portable. So there's no reason to stick to Intel 64, use ARM, use PowerPC, whatever you have available. Part of the question is, would be nice for hardware programming. Well, the thing is, the extension module that you get is tied into CPython or into Python. We do support PyPy. We also support a couple of other runtimes. But in any case, you need a Python runtime around it. So it's not like you can generate code from it and run it on some minimal little device. You need at least something that runs Python. And MicroPython is not currently part of that list. No. Yeah. Okay. I mean, MicroPython is very different from CPython, has a different API, so supporting that would be at least not trivial. There's probably ways to do that, but it's not trivial. Okay. Okay. You've already seen how to use C functions in Python. So instead of using the Python sign function and I can compile that. Okay, still using the Python sign function. What I do now is I take that, I take the C sign function from libc math, assign it to a Python variable, and call that instead. And now that gives me a Python callable function, right? So that actually calls libc sign, libc math sign, right, internally. So that happened because, I've been assigning a function, a C function, to an object variable, and that automatically generates a wrapper for it. Very nice little feature. What happens inside is basically this. So I import libc math, and then it generates a Python wrapper function for me, which internally calls the C sign function, okay, and just passes through the argument to whatever that function accepts, and passes back whatever that function delivers. Okay, so that's what this little shortcut here does. Okay, just to show you that that's really as trivial as it is, the sign function here just says sign of x, calculates that, and then, as you can see, automatically translates the result, the C double floating point result, back into Python object. Okay, so that's done automatically for you. So in Cython, you rarely have to take care of explicitly converting C types from and to Python types, right? That's one of the, main language features that Cython provides. Okay, it becomes a bit more interesting now that we have our own function here. If you add a bit more functionality into this, I mean, this is just a boring flat wrapper around a C function. You probably want to implement a bit more there, and it's really encouraged because that's the layer where fast stuff happens, right? So anything that's Cython compiled turns into C. And so this is where you can do fast interaction also between different C libraries, for example, and we can do data preparations and all this that you want to do outside of Python, because processing data in Python and plain Python isn't exactly the fastest, and unless you have a matching SciPy or NumPy function for it, it's probably better to drop that into C and have it run fast there. So just sign of x square looks like this, as you would expect. You can also just say x times x, obviously, right? And then when I run this, it gets the expected result. Okay. Okay, for a longer example. Everyone likes taxes, right? So here's a nice example that Caleb Hatton presented at PyCon Australia in 2015. I like that so much that I adapted it. And, here's the tax calculation. We're going to calculate the average income of 44 million earners, taxpayers in Germany, how it was back in 2016. That is the average, and now how do we get there? Okay, I was looking for official data that I could use here, like what's the income distribution overall? I have no idea exactly. So there was no way to find that, probably for privacy reasons. And so lacking official data, I'll just create some alternative facts like everyone does these days. And here's some log normal distribution. Let's see how that looks. In matplotlib, it's just a random log normal distribution, and that is it's not too far from what you would expect from an income distribution. It's kind of, well, not so far. Okay, so let's calculate everyone's taxes, right? 44 million. Okay, that's a bit too much to have it run like really fast. Let's take a bit less. 20th of that should be enough for this talk. And so when you look up the income tax, so what used to be the case, I looked that up now, what used to be the case in Wikipedia, they would give you an Excel formula for this, right? Looking like this. Wonderful Excel, right? Now they don't do that anymore. I looked it up again these days. So back in 2016, 17, when I did this the first time, that was still the case. Now they just give you a math formula, which looks kind of mathy and not so messy as Excel. But that's how it looked like back in the day. And so I can translate that into Python function pretty much straight away. And you can see that there are certain ranges in which the tax is calculated in different ways. And they just chain nicely into a continuous graph, but with different properties along the way, right? So if you're very rich, then you pay a higher tax on like higher tax percentage than someone who's normal taxpayer. Okay. To get the average, we then just sum up our incomes and divide it by the number. And to get the average tax rate, we can sum up the tax for the incomes and then divide that by the number of incomes. Okay, so pretty straightforward. Let's see what that gives. We calculate the tax rate. So the tax for the average, okay, that's 10,000 euros. That's the average taxpayer would pay. We keep our data both in a NumPy array and in a list. And since we're processing in Python here, let's do that all based on the list. And then let's see what the average tax is. Yeah, so there's average tax rate apparently is 24%. Okay, that's for the fake data that I use here. Okay, fine. So then let's see how long that takes in Python. It's going to take a couple of seconds to do the calculation, as you just noticed. But let's ask time it how long it takes exactly. Longer than you would expect, right? It runs it a couple of times in case you don't know time it. Time it is really nice for benchmarking stuff. It just runs it a couple of times, then shows you the nicely aggregated result from the. Okay, it takes a bit longer than you would expect. I have a little function here to make all this the benchmark results comparable. You see what that gives in a minute. It's just basically comparing, so it's calculated the ratios each time that I get an improvement, right? So what I'm going to do now is I'm going to take this function and look at different ways how to make it faster. So that took 6 seconds overall. So it had 7 runs, right? So that's why it took so long. It took about 6 seconds to run the whole thing, okay? So I ask my ratio function, and you can see the Python version, well, that's factor 1 compared to the Python version. Okay, yeah, well. Okay, NumPy, what can NumPy do for us? It's a function that has different areas of calculation, as I said. So in NumPy, you could do something like this, where you say, I'm slicing the NumPy array and then do different calculations on that. And in the end, I just sum it all up. Okay. Then it should give the same result. You still see 24%. Wonderful. And then when I ask how fast that is, you can see that it's a lot faster already. So it's 28 times faster than the Python version, right? So this is how the ratio basically works, right? So now compared to NumPy, Python is 28 times slower. Now there's a different way to do this in NumPy. I could just take my Python function that I've implemented and throw it on the NumPy array as a so-called ufunc, which is basically being applied to all values in the array. And NumPy allows me to create such a ufunc with the from pyfunc function. And then I can do the calculation on the whole array. I still get 24% for the average text rate. And now I can ask NumPy, I can ask time it, how long NumPy takes for this to compute. And you can see it's obviously slower than the plain NumPy version. Well, not so obvious, but like in this case, relatively obvious that it's slower because there's a lot of Python code running in the function, and the NumPy implementation, the slicing implementation, is relatively efficient in comparison, right? So even the ufunc function, though, is still more than 3 times faster than the Python version, the plain Python version, right? Also very nice. So enter Cython. This is a plain copy of the Python code that we had above. Literally just renamed the functions so that they are distinguishable. And now I can compile the whole thing, run it, see if the result is the same. And yeah, 24%, wonderful. And now run time it over it to see what Cython made of this. And you can see it also still takes a while to run. Maybe a longer while. I mean, literally what I changed was I added this percent Cython here to make this a compiled cell compared to the normal Python cell, right? Okay. Yeah, you can see it's not very fast. Time it again, runs it a couple of times. And then we can see, yeah, so compared to the Python version, that's actually slower. That is surprising. That's I'll just run it again, as every good benchmarker does. If the timings are not as you would expect, you just run it again. And while that is happening, I can show you that you can also use the Cython compiled version now as a ufunc by just passing into the from pyfunc function in NumPy, right? And then when the above is done, I can show you that the same now works not just using the Python implementation of the function, but also the Cython compiled version of the Python function, right? And then you'll see how long that takes to run. You'll also notice that this is not very fast, but it's supposed to be at least a little faster. Well, that's very close. Usually it's more like, so the compiled version should be more like 15%, 20, but sometimes 30% faster than the plain Python version. That's what Cython usually gets out of it. Okay, not in this case, bad luck for today. I'll try again tomorrow. And now the ufunc is also run, and there you can see that that actually got a bit faster. So that's the plain Python ufunc, and this is the Cython compiled ufunc, exactly the same implementation, just compiled by Cython, and that runs something like, what, a third faster, right? Okay.
There was also another remark in the chat. Someone asked if you compared number with the benchmark.
First question was, what happens if the compiled Python function calls another Python function? Nothing special, I would say. So, I mean, so in Cython, so as I said, Cython compiles Python code, so you can do anything in there that's, normal Python features, Python language features. And that includes using anything Python. You can use dicts, you can call functions, you can use the standard library, anything. It's just plain Python. There's nothing special about Cython code except that it is compiled in the end. The second question was, how would number compare to the benchmark? Well, certainly differently. Also PyPy, obviously, so any JIT compiler would benefit from run this a lot of times over the length of the array, right? So JIT compilers would automatically optimize the code for you here. What I'll do is I'll manually optimize the code. So in case you haven't heard of NumPy is also, well, it's an LLVM-based JIT compiler for Python. You can also throw, mostly Python code in there. It doesn't support all features as Python and Cython do. It's limited, but that's usually okay for, math kernels running computations on arrays, which, use a limited Python feature set anyway. So if you just want something running fast quickly, try NumPy, sure. If you want something to distribute, if you want something that you can tune yourself, that you have that you can get your fingers in and do your own tuning, Cython is definitely the tool for you. Okay, so as you've seen, well, it gets a bit faster, more or less, but it's not really that great. So let's use what Cython is good at, static typing. Okay. First thing we can do is we can make that text calculation function C-callable, because it's only used inside of our module. So making it callable fast, since when we're calling it a lot of times, that makes sense, right? Then we can turn it into a C function by typing our arguments and the return type. And then you can see that, well, the whole rest basically is just computation, so that will unfold into a C implementation. And then here, what I also do is I unpack the sum loop into a more C-ish looking loop. So I do my own calculation here instead of calling sum. And that's also turning into a C loop. Then, so first thing you can see here is, I didn't say what yellow means. The more yellow, the more Python interaction you have. But since this is now all white, you can immediately see that it's all running in C and no longer using any Python objects. And you can see that here. So income greater than this, then do that. And here's the calculation. Also becomes plain C code. So this is a C function now, right? A plain C function. Also the loop down here, we're still using a Python list as input. So iterating over that list needs some Python interaction in order to get at the items of the list. But then afterwards, since I said that X is supposed to be a C double variable here, the values from the loop, from the list immediately get unpacked into a C double. And then this calculation afterwards here happens all in C. I call my text calculation function. I call my add the total incomes, and then in the end do my end calculation. And the result then needs to be converted back to a Python float object in order to return from my function. That's it. Okay, so that's compiled. Let's see what that gives. Still gives me 24%. That's the right result. And now you can see that we've already surpassed NumPy by a factor of 3, right? Simply by typing this, we are now 3 times faster than the original NumPy slicing version, which obviously is a bit hindered by the fact that it does a lot of separate operations, so many separate calculations overall, which here in this function we can do in basically in one go in C. Okay, so also notice that we are now 88 times faster than the Python version. Okay, we didn't really change much in the code, right? So the implementation here is still more or less exactly the same. I just added a couple of types, made it C callable, changed the looping function overall, the looping code. Okay, that changed, right? But not the text calculation function. And still, 88 times, that's okay. Not too bad for doing a bit of work. Okay. Still, we can also use the typed Cython function as a ufunc now, and you'll notice that that is again a bit faster, but not comparable to the plain Cython looping version. It's still, something like close to 8 times faster than Python. It is, here we are. It is definitely faster than the original ufunc version and also the compiled ufunc version. So typing that gave it another advantage of 1/3, but it's still slower than the slicing NumPy version, but not too bad. Only by a factor of 3 to 4. Okay, and still typed Cython beats everything here. Okay, let's make that another bit faster by switching from a list as input to, back to NumPy arrays through the means of typed memory views. So typed memory views are a feature in Cython that allow you to unpack C memory buffers, so native memory buffers. That's usually a NumPy array, but can be anything else, including byte strings, including struct arrays, whatever, right? Whatever you can have in C, and that is provided by a Python data type, can usually be unpacked into a C buffer and then efficiently iterated over by Cython. Okay, so again, our text calculation function does not change. Same thing as before. What changes now is the type of the input argument, the overall input data that comes in. Instead of keeping that a plain Python list, I now say I'm now going to pass the NumPy array, and I'll type it as a one-dimensional C double array. Okay, that's pretty much the NumPy data structure that we have here. One-dimensional. If it was two-dimensional, I would just say comma colon for 3-dimensional and so on. And so this is one-dimensional, and double just says, this is C double. I should actually say Cython double. Doesn't make a difference because I'm compiling. It would make a difference if I was running this in Python. Then it would complain that the name double is not defined. So up. Now I can iterate over this memory buffer and then do the, the adding, the text calculation, and all that. I'll compile this. Takes a bit longer to compile because it's more complex code internally. Shouldn't take that long. Usually doesn't take that long. Bad day today. Okay. There it is, and now it ran, and you can see that compared to the typed list version, it's another factor of 3.5 faster. Okay. Very nice. Still gets the same result. And now we're down to 20 milliseconds overall runtime for all the data that we had. Still, we can make that faster by parallelizing. Since we're doing the same operation across a large array, we can do that in parallel and have multiple threads run on it. And in Python, you can use Python threads for this. Cython has its own syntax feature, which internally does not use p threads as Python threads would, or native operating system threads, but OpenMP threads, which are then mapped to lower level threads in the system at the C compiler level. Okay. Cython can use those through the means of a construct called prange, which is just parallel range. So whenever you have a range loop and want to parallelize it, you can say, I'm going to change that to prange. Then you should release the GIL. The GIL, the global interpreter lock in Python, which makes sure that concurrent threads do not corrupt the interpreter state. And since we're not dealing with the interpreter here, we can release the GIL. We can just say no GIL true. And then inside of the prange loop, everything will run nicely in parallel. And yeah, and then we just read the value from the array, sum it up, calculate the tax, and in the end add everything. One thing you probably notice if you've ever dealt with OpenMP here, I just say income plus equals x, right? And if you think that this is a parallel loop, how does that even work, right? I have just one global variable and everything's summing that up. Doesn't that corrupt the state and lead to parallelization issues? Well, no, it doesn't, because Cython is smart, and when you have plus equals or plus multiply plus minus something, minus equals, like the in place operators in Python operators, right? Whenever you're using those instead of p-range, then Cython will assume that this is an aggregation. And it'll just generate aggregation code for you, just thread parallel aggregation code, right? Very nice. So I run this and see how fast that gets. Hope it's a little faster. Well, not much. Should run it again. I mean, yeah. So you see that here the differences. Well, we're already down to 20 milliseconds runtime already. So I'll just run it a couple of times and see what that gives. If there's anything reasonable in there. Does it stays the same? Yeah. So I have 4 threads on my machine, but only 2 cores. Using hyperthreading, right? And so this should be more or less 2 to 2.5 times faster. I can assure you that it is. Usually, not today. Gives the same performance here, more or less. But yeah, usually it's like 2.5 times faster. That's what hyperthreading gives me. Okay. You probably won't believe me, but if you run the notebook on your side and you have more cores, you probably see a difference. One last thing that I can show you. You remember the NumPy version that we had? The slicing version. There's a tool in Python, it's called Python, and Python is a compiler for sort of a static compiler for NumPy expressions. So it understands NumPy expressions, well, to a certain extent. There are some constructs that you can't deal with, but otherwise it understands them and can translate them into C++ code. So it generates C++ expressions from NumPy expressions. So really native code that also vectorizes nicely and so on. And so Cython comes with Python integration. I can just say Cython np pythons and numpy python equals true. So that enables Python support in my Cython cell here, also in the Cython module. Just add this comment at the top. And then you can see when I run this, it gets a bit faster, should get a bit faster, yeah, than the NumPy version. So there's a factor of 2 in there, which is because a lot of this is still running in Python. So all this summing here actually does not use C++ constructs. That's passed into NumPy again. But when you look at this, you can see that at least some of this should translate into Python. Yeah, right. So I mean, up here you see the Python generated code. Right. So there's a couple of funny operations here. Yeah, and you can see that gives you, well, it gives you a factor of 2 in this case. It might give you better improvements depending on what code you throw at it. But the nice thing really is that you get statically compiled C++ code out of normal, regular NumPy expressions, and you can play around with them, see that Python gets you better code out of this in some way or another, and then just use them as you would write them in Python. Okay, then I would actually stop here and leave the rest for open questions. So yeah, someone said WebEx uses a lot of CPU. Might be. That might be one of the reasons why the timings are, well, not so accurate today.